Hi, and welcome to the July 1st edition of According to Pete. Today we're going to talk about inductors. I've always wanted to do an episode on inductors because I think they're cool. Honestly, I think they're becoming a little bit esoteric for a lot of our applications. You don't need them that often, but we're going to talk about it anyway. And I think you'll dig it. I hope you'll dig it. In the episode after this, 2 weeks from now, we will talk about the projects that I mentioned in the last episode a little more in depth. I'm going to present you with the raw materials to each project and go, okay, here's what this project is, and this is what has to happen, blah, 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 blah. But honestly, I think I've already made up my mind which one I'm doing. I'm going to present all this stuff to you and then wait for comments and then ignore what you say and do what I want to do anyway. Let's talk about inductors. Let's say you have a wire, and I got to start very, very basic, okay? Cross-section of a wire. This is what we're looking at here, okay? Electricity and magnetism have this funky relationship, you see. For example, let's say that I've got current going into that wire, right? If this was a dot, current would be coming out. In this case, we're looking at the feathers of an arrow, so it's going that way. Now, there's something called a right-hand rule, which indicates that your thumb points in the direction of current and your fingers point in the direction of the magnetic field. So by the way I've drawn this, what happens is you will get a magnetic field around the conductor, not inductor, conductor. This is a wire cross section, right? Okay. From t equals 0, right? Time equals 0. When you first apply current to this wire, it starts out slowly and it builds up and then it stabilizes after a period of time. And the reason that occurs is because of another property that magnetism and current flow have. How do I explain this? Well, when you have a magnetic field that cuts across a wire, a conductor, it actually induces a current flow in that wire. From t equals 0, what happens is current will, I'll just do a little plot here, current will very slowly sort of kind of ramp up, whereas the voltage across this thing actually starts out very high and gradually goes to 0, okay? It represents a resistance at t equals 0, and as the current stabilizes, the resistance goes to just the DC resistance of the wire, okay? So this is our inductor. This is a conductor. This is our wire that makes our coil, okay? And I got current going through this thing, and so there will be a magnetic field, sort of like that, and it'll go this way, and then back around there, like that. Okay, so this is an inductor. Now, an inductor stores energy in the form of this magnetic field, right? Here's the trick, and it resists current. Here's the trick. When you first apply current, like I said, it will resist the current change. This thing, what it likes to do is like maintain a constant current through it, whether it's 0 current or 1 milliamp or 2 milliamp, whatever. It's going to try to maintain it. Because once you take away the motive force, like if I had a battery on this would be the condition. If I took the battery off, all the energy that's stored in this magnetic field will collapse down, and as it does so, it cuts across the wire and induces that current to keep going. And I got an example that I'll show you later on at the end of this, I hope. It stores energy in the form of the magnetic field, and it resists a current change, okay? L is the symbol for inductor, and it's actually measured in henries, but L equals, and I got this equation here, mu naught, and mu is like that, times a n squared. I'm going to explain this, be cool, over, that's a bad script, L. Okay. What this says, and a lot of you know this equation probably, is that the inductance of an inductor, because that's what it is mu naught. Mu naught is the permeability of air, and I'll explain that in a second, times the area. The area is like the area of the circle, like this forms a cylinder. Actually, the term is a solenoid. I'll explain that later. I'm going to explain a lot of things later. The area of this cylinder, right, so like yay big or so, times the number of turns squared, okay, divided by the length of this thing. So A is like the area of the cylinder. L is like from here to here, okay? What these terms say is that the longer the inductor is, the less inductance it's going to have, okay? The greater the area, the cross-sectional area of the cylinder, the more inductance it's going to have. And of course, the number of turns increases the amount of inductance as well. Okay, now let's talk about mu naught. Permeability. This is a material's ability to focus magnetic flux, magnetic lines of force, okay? For air, it is effectively 1, and mu naught means like, you know, air. It is mu naught is, for all intents and purposes, 1, okay? So you can, if this is an air core inductor, you can pretty much neglect that term. Now, there are other materials that you can use, ferrous materials, for example, iron stuff, that if you put in the core of this thing, will dramatically increase the amount of inductance this has. And when I say increase inductance, I mean it is able to focus more magnetic flux, it will store more energy, it will resist current changes more. Okay? So these are the terms that go into what makes an inductor be an inductor. Not all inductors are of the solenoid form. Like I said, this is a solenoid, not like the thing that opens your locks or what have you. This is just a cylindrical inductor. With regard to permeability, and I said ferrous materials are really good, there's also there's some really crazy stuff out there that is much better than like iron core. And there's a lot of science that goes into this because you get eddy currents and stuff inside the core material, and that ends up being a loss. We'll talk about losses in a bit. As I said, when the magnetic field cuts across a conductor, a wire, it induces a current, okay? Now, inductance is effectively, really, it's an AC property. It's something that you care about for alternating current, right? There are DC uses, sort of, but they all come back to AC. Because if you just put a current, a DC current through this thing, all it's going to do is maintain a static magnetic field. And that's not necessarily very interesting, unless you're making an electromagnet. When you're using these things on a circuit board, if you had just like, you know, a coil with a piece of iron jammed in it, and you were using this for an AC purpose, effectively what this thing is doing is that at some frequency of interest, it is expanding and contracting a magnetic field. That magnetic field will a lot of times cut across your other circuitry and induce a bunch of junk that you don't want in there. That is called flux leakage. And so for a lot of reasons, well, for that reason, they design inductors specifically to maintain the flux. Maintaining the flux makes the device a lot more efficient. It makes it quieter, which you need it to be quiet. What they do, there are a couple of different techniques. One thing that they do is they will put it on a toroid. And this isn't like the best thing to do, but they'll wind like an inductor like this. All the RF guys know this because they make chokes and stuff. I'll talk about a choke in a minute. But this maintains the majority of the magnetic flux within the core material because it's the permeability of this material is a lot better than the permeability of air. And so the flux will tend to stay inside the more permeable material. But it's not a perfect solution. So a lot of times what they will do is they will put a can of sorts around the inductor, and the can is made of a a magnetic material, a ferromagnetic material like iron. I'm sure they don't use iron, but they use a material a material that focuses magnetic flux, because, as I said in this example, the flux will tend to stay in the material that is more permeable. It will not go out. And so, and I'll show you this. I have to go find it, but I've got a transformer that's got a can on it, and it's pretty cool. And the whole reason for that is so that it maintains the flux within it. So we've talked about inductors a bit. Now let's talk about transformers, which is actually sort of kind of two or more inductors. This is a transformer with a core, iron core, let's say. The crazy thing about a transformer is that if you apply, for example, a 60 hertz signal, 60 hertz going in here, you will get 60 hertz coming out of here, right? Because this is creating a magnetic field that oscillates at 60 hertz. The field is focused in the core material, and it's inducing the same thing in the other coil, okay? Inductor, coil, inductor. Meh. And this is why it's cool for AC, because you can do this stuff. Now, why do you want to do that? Well, check this out. Let's say I've got, for example, 10 winds, right? 10 turns of the wire around a common core of the primary. This is called the primary. P for primary, S, secondary. So if I've got 10 turns here and I got 20 turns here, I get twice as much voltage out of here. So if I've got, for example, 10 volts, and this is just arbitrary choosing that. I know, 120 RMS, 169 peak to peak, blah, 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 blah. Let's say I got 10 volts peak to peak going in here. I get 20 volts peak to peak coming out of here, because this is twice as many turns, okay? Now, the thing to note is that if I've got 10 volts and 1 amp going in here, I do not have 20 volts and 1 amp coming out of here. I have 20 volts and half an amp, okay? Power in, this is important, power in equals power out, ideally. In fact, in truth, it really is P out equals P in times some kind of efficiency factor, okay? These things are never perfect. You will never get, if I'm putting 10 watts in here, I'm never gonna get 10 watts out. Ain't no way. And the reason is because you get losses. There's like DC resistance in the coils, right? There are losses in the core material. And remember I said a little bit ago that they get eddy currents and stuff. Let me show you an example of a couple of transformers that I have here. Here's a couple of examples of transformers that I've got lying around. And they're actually both for tube amplifier projects. This one from Hammond, right? The things worth noting here, first of all, you'll notice the cans. Remember I was talking about how you get flux leakage, right? And so they surround all the windings with a ferrous can. I'm pretty sure it's not iron. I don't know what it is, but it'll focus the magnetic flux enough that it really doesn't leak out of here, so it doesn't jack up the rest of your circuitry, okay? Now, also worth a mention, I talked about losses and eddy currents in the core material, okay? Let me try to describe that. What happens, right? The core material is ferrous, okay? Ferrous material conducts electricity. And if you have a magnetic field that's cutting across that material, it will induce a current. That ends up being a loss, and that's why you never get the same power out that you get going in, okay? So what they do, and I'm not sure if you can see this very well or not, but what they do is they take the core, this is the core, right here, and all the windings are inside there. They will actually split the core into very, very thin slices of material, and they will laminate them all together with an insulating varnish, okay? In that way, they can still maintain the permeability of the core, but sort of try to keep the eddy currents from getting around to all the layers, right? You can still get currents like in the individual layers, and they're very thin. I mean, they're like 0.5 millimeter or something thick. They're pretty thin. But that's why they do that, to improve the performance of the transformer. Now, here's another one. This is on the toroid. Remember I described that sometimes I do that? Well, here's an example of that. It looks like there's like one primary coil that's going to be the black and the white, almost certainly. And this is supposed to drive a tube amp, so it'll have like a 6.3 volt at a high current and then a high voltage, so there'll be a lot of winds to do that. And for the project that I'm talking about, I actually have 4 different transformers that I meant to gang together to get the voltages that I wanted. But the point is, here's an example of a toroid transformer, right? There are several different coils wrapped around the toroid. Now in this case, they don't have a can. They're intending to focus all of the flux within the core material. Now, how do they deal with eddy currents for this? Well, the material is like powderized and then powder cast, and so it's actually not like a solid conductor, not a solid ferrous material, so eddy currents don't really form within the core material. Yet it still maintains the ferrous property that allows it to focus flux, okay? Now let's hit the board again. Okay, so something I probably didn't explain very well is the turns ratio and the voltage. So I'm just gonna spell it out right, which I should have done in the first place. Let's say you've got N1, N2, and what this is like, number of turns. So the number of turns in the primary, number of turns in the secondary. Now how this relates to the voltage in versus voltage out is a ratio. So N1 over N2 equals V1 over V2, okay? It's a ratio. And it's about as simple as it gets, right? If you've got twice as many winds in the secondary as you do in the primary, you're gonna have twice as much voltage on the output, okay? Current is the opposite, right? If you're doubling, power out equals power in times the efficiency, right? So if we say that efficiency is 1, then power out equals power in, which never happens, but for the sake of argument, we're gonna say it does. So if the voltage is doubling here, the current has to be half in order for the power to be the same, yeah? Remember that. Now, impedance is also something that we should talk about. Okay, and this is not DC resistance. This is if you're matching AC loads. And this is something I gotta do for my tube amp junk. And I wrote this down. So you've got a characteristic impedance at some frequency going in here, and you've got a characteristic impedance that you have to match on the output. And the way this is like N1 over N2 squared, that's a really bad 2, equals Z1 over Z2. And Z is the letter for impedance, where R is resistance, Z is impedance. It's an AC thing, right? So this will be Z1, and this will be Z2. Better Z. I need to practice my Z's. So where do you see inductors? Well, the first example is in a switching regulator, right? A buck regulator. So it's switching from a high voltage down to a low voltage. And they're used in boost regulators too, but this is the example I'm gonna use. So a very basic drawing of a buck regulator is like, yay. And that's your input. Here's your inductor. There's a cap there. And this is that's ground. I don't know why I did that. I always do this junk. Okay, so you've got a high voltage, right? This is the way your buck regulator works, right? This is your signal in at some voltage, plus V, I don't know. So what happens is, right, you apply a high voltage here, And there's actually a feedback network here that'll go back to whatever it is that's sensing this, okay? So what happens is it turns on a high voltage here, and it charges this guy up to a point, right? This is your V out, whatever it happens to be, and it's measuring this, right? And as soon as it gets to a certain point, it shuts off. Now, what this inductor does, right, when the current's on, it's slowly ramping up, okay? It's resisting the current change. It's slowly ramping up. Well, slow is like microseconds. It's some people that's slow. And when the device that's doing the switching senses that the voltage is high enough, it turns this off, okay? This voltage goes to 0. What happens then is the field starts to collapse and the current conducts through this diode, okay? And it starts to ramp down. And this is just repeatedly all the time, forever and ever, amen. That's why the diode's there. That's why the inductor is there. And the cap just smooths all this junk out, okay? Now, for you guys who know these regulators in depth, hey, come on, man, I got 20 minutes to do this. But that's effectively what an inductor is doing in a switching regulator. Okay, so another application is an RF choke, radio frequency. Let's say, for example, you've got, some circuit out here that generates a whole lot of radio frequencies, and you are supplying it, plus V to whatever, from a power supply, and you don't want all that noise getting back into your power supply. Well, what you do is you put an inductor there, okay? Now remember I said this thing opposes changes in current, okay? So this thing is generating all kinds of noise, but this thing is basically squashing all of that noise because it's trying to change the frequency of the current really fast, and this will just filter it all out. All the noise gets canned in this thing. That's called an RF choke. It's choking the RF. Another application is an electromagnet, right? I don't have to draw a picture of this. Basically, you take a whole bunch of wire, you wrap it around a nail or something like that, and you pass a current through it, and you get magnet. How easy is that? Not an AC function, but, magnets are cool. We like magnets. This one you can turn on and off. So that's, something else. Speakers. Speakers have big coils in them, right? They've got a permanent magnet in them, and Robert will get on me for this, I'm sure. But there's a big coil inside of your speaker that's surrounding a permanent magnet. And as you apply an AC current to this thing, it causes the coil to vibrate against, the cone of paper, and it generates sound that way, okay? That's, another application. Pickup coil. I love this. So I made a while back a pickup coil made. This is a parts reel, right? And what I did was I took some styrofoam and I wound it around, or I hot glued it into the channel so that it was only like maybe an inch deep or a quarter inch deep. Wrapped a whole bunch of wire on this thing, and then I tuned circuits. I'm going to get to that in a second. I tuned it with a cap for like audio range, like 1000 hertz or so, hooked it up to an op amp and some headphones, and suddenly I've got a pickup coil where I can hear people's TVs and stereos and all kinds of electric junk that happens at audio frequencies because it turns into this giant pickup coil. Okay, that's another thing you can do. Now that's not a standard application, that's just some junk I made up, but kind of fun nonetheless. And then there's tuned circuits. Tuned circuits are things that are used in RF a lot, and I haven't talked about this, but when you take an inductor, a really bad inductor, and you mate it with one of these guys, you get something called a tuned circuit. This is a parallel tuned circuit. Now, the thing that I never talked about is that current and voltage are 180 degrees out of phase from each other on these two devices. And so when you get them together, really wiggy things start to happen, and you can get really cool oscillating, and in some cases, really bad oscillating. And this circuit by itself really demands its own episode. Something I've never spoken about with regard to capacitors and inductors is how Eli the Iceman, voltage leads current in an inductor and current leads voltage in a capacitor. It's a phase relationship thing, and when you get these two things together which have opposite phases, very strange things can happen. Really cool things can happen. RF guys know all about this junk. But I've never talked about that. For a lot of the purposes of our customers, well, I really shouldn't go assuming what our customers do, don't know, and want. But we've barely scraped the surface of both of these components. And when you get them together, parties happen, and it's wacky. So that's gonna wrap it up, guys. I hope I said something intelligent. In case I didn't, I'm sure somebody's gonna tell me what I screwed up. In 2 weeks' time, we will talk about projects. I'm gonna wheel some stuff out for you and say, hey, look at this, man. Like that. And then I'm gonna figure out what I'm gonna do, although I already think I know what I'm gonna do, but we'll see. Keep the comments coming, keep the questions coming, comments below, or you can send them into feedback@sparkfun.com, according to Pete in the subject line, and I will see you in 2 weeks' time. Bye.